By the end of this video, you should be able to calculate the lattice energy from the enthalpies of the steps involved with the ionic compound formation. Let us say we want to prepare 1 mole of solid sodium chloride in the lab. What we do is we start with sodium and chlorine in their standard states, put them in a container and initiate the reaction. The standard state is the physical state of an element at room temperature, that is 25 degrees Celsius, and atmospheric pressure, that is at 1 atmosphere. The standard state of sodium is sodium solid and chlorine is Cl2 gas. This reaction is called the formation reaction, and the energy change associated with this reaction is called as formation energy. Formation energy is defined as the change in energy when 1 mole of a substance in the standard state is formed from its pure elements under the same conditions. The important thing here is that only 1 mole of the substance should be formed. So for 1 mole of sodium chloride to be formed, we need to start with a half a mole of Cl2 gas. The formation energy can be measured in the lab, and its value for sodium chloride is minus 411 kilojoules per mole. What we are going to do now is break this reaction into several imaginary or hypothetical steps and try to calculate the energy cost for each of these steps. First, sodium in its solid state is converted into a gaseous form. The physical process where you convert a solid metal into gaseous metal atoms is referred to as sublimation or atomization. This process usually requires energy, and the energy required is called as sublimation energy or atomization energy. For sodium, the sublimation energy is 107 kilojoules per mole. Next, the gaseous sodium loses an electron to form a monopositive cation, and we know that the energy required to remove an electron from a gaseous atom is called as its first ionization energy. For sodium, ionization energy 1 is equal to 496 kilojoules per mole. Next, let us look at chlorine gas. Chlorine exists as gaseous Cl2 molecules inside the reaction container. First, we need to break the bond between two chlorine atoms. We have half a mole of Cl2, so we get 1 mole of Cl atoms. The energy cost for this reaction is called as bond dissociation energy. Usually, the bond dissociation energy is given as kilojoules per mole. This is the amount of energy required to break 1 mole of bonds. For chlorine, the bond dissociation energy is 242 kilojoules per mole. In this case, however, only half a mole of bonds are being broken, so it costs half as much, that is 121 kilojoules. Once we get gaseous chlorine atoms, these chlorine atoms gain an electron to form chloride ions. And we know that the energy change that occurs when an electron is added to a gaseous atom is defined as electron affinity. Electron affinity of chlorine is minus 349 kilojoules per mole. This step releases energy, and the negative sign represents that it is releasing energy. Now we have 1 mole of Na+ in the gas phase and 1 mole of Cl minus in the gas phase. They attract together to form 1 mole of solid NaCl. The energy released in this process is called as lattice energy. Lattice energy is defined as the energy released when 1 mole of ionic crystal is formed from its cations and anions in their gaseous phase. Lattice energy for sodium chloride is minus 771 kilojoules per mole. That is, the energy is released. Now let us write all these steps together. These individual reactions are steps involved in a bigger reaction, which means that the products of one step are the reactants for the next step. Therefore, if we add all these individual steps, we get the final reaction, which is the formation reaction of sodium chloride. The interesting thing about the delta E values is that they are called as state functions. You don't have to know what it means now. We will discuss this in the next semester in a great detail. What you need to know now is that when you add two or more equations to get a final equation, then you can add delta E values of individual equations to get the delta E value of the final equation. Therefore, if we add all the energy changes of the individual equations, we get the formation energy of sodium chloride. The same set of equations can be shown in the form of a thermochemical cycle. Imagine we are plotting the energy change of the reaction mixture on the y-axis. We start with 1 mole of solid sodium and half a mole of Cl2 gas. Let's assume that this mixture has some amount of energy associated with it. The exact value of the energy is not necessary. When these reactants react to form 1 mole of solid sodium chloride, which is the product, 411 kilojoules of energy is released. Therefore, the 1 mole of solid sodium chloride sits 411 kilojoules below the reactants of the reaction. The negative sign represents we are going downhill in terms of the energy. Next, we break this reaction into several steps as we did before. First, when sodium in its solid state is converted into gaseous form, 107 kilojoules of energy is absorbed. Therefore, the energy of the reaction mixture increases by 107 kilojoules. That is, relative to the reactants, the gaseous sodium and Cl2 gas sits 107 kilojoules higher. Next, when gaseous sodium loses an electron to form gaseous Na plus ion, the reaction mixture absorbs energy that is equal to its ionization energy, which is 496 kilojoules per mole. The energy of the reaction mixture goes up by the same amount. Next, when half a mole of gaseous Cl2 inside the reaction container gets converted into 1 mole of Cl atoms, the reaction mixture absorbs energy equivalent to that of half of the bond dissociation energy, which is 121 kilojoules. The energy of the reaction mixture goes up by 121 kilojoules. Next, when 1 mole of gaseous chlorine atoms gains an electron to form gaseous Cl minus ions, the reaction mixture releases 349 kilojoules of energy. Again, the negative sign represents that we are going downhill in terms of energy. Next, when 1 mole of Na plus in the gas phase and 1 mole of Cl minus in the gas phase combine to form 1 mole of solid sodium chloride, the reaction mixture releases energy that is equivalent to lattice energy, which is 771 kilojoules. So, if we add all the energies in the cycle, we get the formation energy. If we look at this thermochemical cycle or the series of the reactions in the previous slides, we can say that if one of the energy values is missing, we should be able to determine its value from all the other values. This is exactly why we use these thermochemical cycles. Specifically, we use the thermochemical cycle to determine the lattice energy of an ionic compound. In theory, we can measure lattice energy by combining gaseous cations and anions to form an ionic solid and measure the heat released in this process. However, the gaseous cations and anions are extremely unstable, and measurable quantities of the gaseous ions have never been isolated. That means there is no practical way to measure the lattice energy of an ionic compound. It is important to know this value because the magnitude of lattice energy is a measure of the strength of the ionic bond, and it gives us information about compounds' macroscopic properties such as melting point, hardness, and solubility. So, how do we determine the lattice energy of sodium chloride? By using the thermochemical cycle or the set of equations used before. This thermochemical cycle is called as Born-Haber cycle, which describes a process in which an ionic solid is formed from its individual elements in a stepwise manner. Construction of Born-Haber cycle can also help us determine the value of lattice energy given all the other energy values. Let us do one example here. Use the following information to calculate the lattice energy of magnesium chloride. The formation energy of magnesium chloride is given as minus 956 kilojoules per mole. The sublimation energy of magnesium is given. First ionization and second ionization energy of magnesium is given. Bond dissociation energy of Cl2 is given. And electron affinity of chlorine is also given. First, let us have a rough sketch of the steps that happen inside the reaction container towards the formation of magnesium chloride. We start with the reactants in their standard states, that is, magnesium in its solid state and chlorine in the gaseous form. First, magnesium solid gets converted into magnesium gas. This process is called as atomization or sublimation. Then, from the gaseous magnesium atom, one electron is removed to form a magnesium plus ion in its gaseous state. This process is called as first ionization energy. Later, another electron is removed from magnesium plus ion to form magnesium 2 plus ion in its gaseous state. This process is second ionization energy. Then we will look at chlorine. First, the bond between two chlorine atoms is broken. The chlorine atoms are in gaseous phase. This is called as bond dissociation. 2 moles of chlorine picks up 2 moles of electrons released by magnesium to form 2 moles of Cl- ions in their gaseous phase. This is called as electron affinity. At the end, the magnesium 2+ ions in the gaseous phase and Cl- ions in the gaseous phase combine to form magnesium chloride in the solid phase, which is the standard state for magnesium chloride. Now let us verify the energy changes associated with each of these steps is given in the question or not. The first step, magnesium solid to magnesium gas, is atomization or sublimation energy. This value is given. The next step, magnesium getting converted into magnesium plus, is the first ionization energy, which is also given. Magnesium plus converted into magnesium 2 plus is the second ionization energy. Its value is also given. Then chlorine breaking into chlorine atoms is bond dissociation energy, which is also given. 2 chlorine atoms picking up 2 electrons to form 2 chloride ions. This is electron affinity of chlorine, which is also given. And we need to find the lattice energy, which is the energy released when magnesium 2+ ion in its gaseous phase combines with chloride ions in its gaseous phase to form magnesium chloride solid. Now let us write down all these reactions and change in energies associated with each of these reactions to determine the lattice energy. First, 1 mole of magnesium solid gets converted into 1 mole of magnesium gas. The atomization energy or sublimation energy is given as 148 kilojoules per mole. So this step costs 148 kilojoules. Next, first ionization energy, which is magnesium in the gas phase gets converted into magnesium plus ions in the gas phase plus 1 electron. This reaction costs 738 kilojoules per mole. Next, magnesium plus gas releases another electron to form magnesium 2 plus in the gaseous phase along with 1 electron. The energy cost associated with this reaction is 1588 kilojoules. Next, the bond between chlorine is broken. That is, Cl2 in the gaseous phase converts into 2 moles of Cl atoms in the gaseous phase. The bond dissociation energy is given as 243 kilojoules per mole. As we discussed earlier, this is per mole of bonds. And in fact, in this reaction, we are making 1 mole of bonds. Therefore, the energy cost is 243 kilojoules. Next, chlorine in the gaseous phase gets converted into Cl- in the gaseous phase. We have 2 moles of chlorine gets converted into 2 moles of Cl-. The electron affinity of chlorine is given as -349 kilojoules per mole. According to the definition, electron affinity is given per mole. However, in the reaction, we have 2 moles of chlorine accepting 2 moles of electrons. Therefore, the energy cost for this reaction would be twice as much. Next, magnesium 2 plus in the gaseous phase combines with 2 moles of Cl- in the gaseous phase to form 1 mole of magnesium chloride. The energy cost for this reaction, which is equal to the lattice energy, is not given. If you add all these reactions, magnesium and magnesium gas gets cancelled. Magnesium plus in the gaseous stage gets cancelled with magnesium plus in the gaseous. Mg2 plus and Mg2 plus gets cancelled. 2Cl and 2Cl gets cancelled. 2 moles of electrons on the left hand side and 2 moles on the right hand side get cancelled. And at last 2 moles of Cl minus and 2 moles of Cl minus gets cancelled. So on the reactant side, the leftovers are 1 mole of magnesium solid and 1 mole of Cl2 gas. And on the product side, the leftovers are 1 mole of magnesium chloride in the solid phase. This is the formation reaction of magnesium chloride, and energy change associated with this reaction, that is formation energy, is given. We know that if we add up the energy changes of the individual reaction, we get the energy change associated with the final reaction. And from this, we can calculate the energy change associated with the sixth step, that is delta E6 or lattice energy. If we do the math, the lattice energy we get is minus 2975 kilojoules per mole of magnesium chloride that is crystallized.